So thank you very much for the organizers for preparing this workshop. And I'm going to talk about some very recent results that we obtained in the quantum software group at Xanadu. And actually, the paper appeared today on the archive. So if you want, later you can check about what's the more details on this. So maybe you know already Xanadu. This is a full-stack quantum computing company that is working on hardware, and they aim to produce optical photonic circuits. And but this, in a parallel way, is working also on software, on quantum software, and in particular on quantum machine learning. And actually, this talk is more about this quantum machine learning side. And these are my collaborators, so Tom Bromley, Josh Isaac, Maria Schuld, and Nathan Killoran. So this is the outline. It will be very introductory because I think the audience is very different. And so I will make a long introduction on what I mean with doing machine learning with variational circuits. And then I will present this new approach of using quantum transfer learning to mix classical and quantum neural networks. And then I will show a practical application of this approach, in particular for the classification of high-resolution images with a quantum computer. So let me start with introducing variational quantum machine learning. So before talking about quantum systems, let me just review what is the standard way of defining a classical neural network. So usually, I think you already know this, you have an input state, an input vector of variables that you want to process, and you can process with many layers of like linear operations plus local nonlinear activation functions. You have many layers of this that you can variationally optimize in order to have good predictions at the output. That's the basic model of machine learning, specifically classical neural networks. So from a mathematical point of view, this is just a family of functions. It's a function C that maps a vector x into y, and is parameterized by many parameters that you can optimize. In the quantum setting, you have something which looks very similar, and is the concept of a variational quantum circuit. So, for example, you can have, in this case, 4 qubits that you can start to parametrically rotate in the Bloch sphere, and this is your variational step. Then you also introduce some entanglement, otherwise the circuit will be too trivial. And then you get the equivalent of a layer that you can repeat many times. And in this case, instead of having a function, you have a family of unitary operators that you can apply to quantum states. But in this talk in particular, we are not interested in processing directly quantum states, but we would like to use a quantum circuit to process classical data. So we have to encode data in the circuit and to take it out. And a simple way to do this is, again, to use a variational circuit, but now the parameters are not the first circuit that you see there. It's an encoding layer in which the parameters are just your input data, is your input classical data. And then the second part of the circuit is responsible for the actual quantum computation that you can train. And this block is exactly the variational quantum unitary that I've shown you before. And then the most obvious way to get classical data out of a quantum system is doing simple measurements. For example, you can assume that you just measure in the Z basis all your qubits. And then you get a vector of classical output. So if you consider as a black box, this actually red box there, it's essentially, it has the same structure of what I've shown you before. It's a function that maps a classical input into a classical output and depends on classical parameters. So from a mathematical point of view, it's not something so different from a classical network. What the difference here is that this family of functions if the system is large, is something that you cannot simulate. And so it's some kind of extra power that you get that could be useful in machine learning. So after this long introduction, let me present a simple model in which we mix a quantum circuit with classical circuits. And the simplest thing that you can do is what we call the dressed quantum circuit. You get a quantum circuit in the middle, and then you put a classical layer before and a classical layer after it. Basically, you have some classical pre-processing and post-processing, and the large part of the computation is done by the quantum circuit. So the two main advantages is that now you have, thanks to these classical layers, a complete flexibility in the number of input and output variables. Sometimes this is hard to get when you work with real quantum systems. And moreover, you can use these classical layers to optimize the decoding, the encoding and the decoding of information. In some sense, the two classical layers could learn how to use the quantum device. And just to give you an example, we just apply this simple model to classify points on a plane. This is a typical benchmark data set that you can test with all machine learning algorithms that you want. And in this case, it works quite well. And the main part of the nonlinearity that you need to fit these spirals is given by the quantum part. But the classical layers are very useful to encode and to decode the information. So, but now let me go to the main idea of this talk, which is related to the concept of transfer learning, which is actually something well known in classical machine learning, but actually it's an idea which was born before machine learning. It's related to how our human brain works, because it's based on the simple fact that it is often very common to use our previous knowledge to learn something new. For example, if you learn a second language, you don't start from zero, learning all the grammar or the concept of words and so on. You use all the previous knowledge and you do a little step further to learn something new. And this idea actually was applied very successfully in classical machine learning, and we'll show you later. And what we want to understand is that if this kind of transfer of knowledge from a physical system, maybe classical one, into a quantum one, is possible using this kind of variational neural networks. So let me define more technically what I mean with transfer learning in the context of machine learning. So assume, I will just show you this picture. Assume that you have a generic data set, dA, and you process it with a generic deep neural network. It can be classical or quantum, and for a given task. And now assume that for some reason you have a new problem, a new data set and a new task that you want to solve, and which is more or less related to the previous one, but it's different. And then you have two options. The first option is to, again, train a very big neural network from scratch, or you can try to recycle what you have learned before. So you take the previous pre-trained network, A, you remove some of the final layers, and you replace them with a new network, B. And then you are going to train only the final part of this network, only the B part, and this can be very small compared to the full network. It can be very efficient, this process. For example, this is an example taken from the PyTorch tutorial that you can find online. You can use this trick to classify high-resolution images of ants and bees. These just two classes of images. And the way to do this is to take a pre-trained, state-of-the-art deep neural network developed by Microsoft. It's a residual neural network with the millions of parameters that you just keep fixed. You don't have to train it. And then you just replace the final fully connected layer, and you train only the final part of it. And it works. You can show online that it works very well. You can see it. And so the what we want to do is to do something very similar using a quantum circuit. So assume that this is exactly an example that we used in our paper. Assume that we replace this final part of the network with a quantum circuit, and the rest is just the same, a big classical neural network that pre-processes your data, and then you want to make classifications. So the question is, okay, this is a big object, quite complex, and how can we train it? Do we have something analog to TensorFlow or PyTorch that is good for quantum circuits? And the answer is yes. This is a new software platform which is developed by Xanadu, and it's an open source library that you can use in Python to perform exactly this, like automatic differentiation, like TensorFlow or PyTorch, but applied to quantum systems. And so we use this, and I will show you the results, which are about this kind of classifications, but done with real devices. So these are just, for the moment, simulations. We used like 4 qubits system, or 5 qubits, I don't remember now, with a variational depth of 6 layers. And we trained this for 30 epochs. And these are the results. You get an accuracy of 97% in the classification of the same images that you can find in the PyTorch tutorial. And we repeated the experiment with other data sets. And also, we applied this on real hardware. And the nice thing of Penny Lane, which is this kind of new software library, is that you can do this by changing a single line of code. You define a new backend, and your model is just the same, and you can run it on whatever backend you want. And these are the results. These are very, from my point of view, these are very good, because up to, so this is, sorry, I have to explain. The first line is the simulator that we have seen before. The second line is the IBM processor. The third line is a processor by Rigetti. And we don't want to make any comparison now. It's just a random example. But I think that in both cases, the results are very good, especially if you think that we are classifying high-resolution images, which was, up to our knowledge, never done using a quantum system. So in conclusions, I presented this idea of dressing a quantum circuit with classical layers, and a theoretical paradigm of using transfer learning with quantum variational circuits. And I've shown you that you can use this trick to classify a large amount of data, for example, high-resolution images, with the current quantum computer. So something that you have already today can classify, can solve problems that are relevant from a practical point of view. So much more details can be found in the paper that is today on the archive. And all the results can be reproduced with the code that you can find at this link on GitHub. Thank you very much.
Thank you. Well, we have a problem with some car. I don't know if it is yours, which is parked not in the proper place, or quantumly displaced from its original position. The car is a Hyundai, and they are about to remove it because it's blocking the traffic. I don't know. No, this is a Volvo. It's not
One is a Volvo.
Ah, there are two.
Okay. There are 2 cars.
One is a Volvo car.
This is the blue car.
Blue
Volvo car.
FT036AD as the plate. And the second one is a Hyundai blue again. There is DA503. Then there is an incoming call. And A3WV. And there is a quantum track that is trying to tunnel it, but is not. So it's not working anyone. So far, it's not able to tunnel the car. So that's a problem. Sorry. Question for Andrea.
Okay, so I have a question. Thank you for your talk. It's well known that Xanadu is developing not only software but also hardware. So my question is not exactly about your talk, about your company. And the question is, can you please provide some updates about the current status of the hardware and if the Q modes are in the silicon chip, and if you have some results about that?
So the simple answer is no, in the sense that I don't know, because I'm working on the software part. But I can tell you that they are doing a lot of progress, and there is also, yesterday there was a new paper about practical applications of photonic circuits, which are the kind of algorithms that they plan to solve in the near term using, in particular, what is called Gaussian boson sampling. So it's you create squid states, and you apply a linear network of interferometers, passive network, and you measure photon counting. This is not universal for quantum computing, but you can solve problems with it.
So,
There was a
hi.
question.
Yeah, it's me. First of all, congrats for your job. Seems very nice. I just want to ask you, as far as I remember, if you just use the classical pre-trained ResNet, you can quite achieve the same performances in terms of accuracy without adding, say, any quantum layer at the end. And I don't think that you have an advantage in inference time because you're adding another layer on top. So I was wondering, which is the main advantage in doing this? I mean, the network should see less samples in order to converge or something like that.
So this is an important question, and so it's true that if you use a classical network instead of a quantum one, instead of basically the green part could be fully classical, you get comparable results. But for us, the fact that you can get comparable results is an extremely positive fact, because up to now, usually you have like kind of toy models in which quantum systems they give good predictions, but you can solve the same problem with a much better precision and accuracy in a classical way. In this situation, we are competing. We are in the same level. Actually, the numbers that we get is like it's like a fraction of 1/1000 better than. So the quantum is a little bit better than the classical, but we don't want to claim any kind of advantage here. We want to say that we are in a situation in which the quantum circuit can compete with the classical one, and we don't know. As I've shown you before, now the circuit is very small, but once you have access to a circuit that you cannot simulate, maybe what this parametric family of functions that you are applying is larger than, for sure, it's different from what you can achieve classically. We expect that for some problems, the quantum circuit could be better. Maybe for others, no. We don't know.
Of course, I agree with you that it's I really agree with you that it's really nice at the moment just to say achieve the same results that the classical one. I was just wondering when this say layer will scale to some other level, which were the expected advantages.
Yeah, I would say that we can expect something better when the quantum system is larger, maybe in a regime in which we cannot simulate it. And moreover, I think it strongly depends on the problem, because maybe what you need is a simple function, because actually a neural network is an approximation of a function. And maybe the function that you need in practice has to be simple, and you don't need a quantum circuit at all. But maybe the correlations which are hidden in the data are so hard to understand that you need a much more complex ansatz for your function. And that's where we expect to have an advantage.
So I mean, you think that you can benefit in terms of accuracy when the task will not be so trivial as say
Yeah,
classifying
this was already trivial from the beginning, but yes.
Yeah, very quick. So is the QPU that you have in this methodology limited to gate logic quantum computing, or can you think also about different platforms? I mean, D-Wave or ion traps or whatever?
So we developed it using the gate model, but in principle, the same trick could work in any kind of system in which you have a variational kind of object. And so if you have classical parameters that you can optimize, then you can use it as a block of an hybrid network.
Okay, thank you. I don't know if there was question from the other room.
Yes.
Yes?
I have a question about the quantum neural network. Since quantum circuit allows only unitary operation, how in quantum neural network the activation function, which has to be nonlinear, is implemented somehow to achieve, the same result in classical one?
So, okay, I understand the question. So actually, in this case, the nonlinearity is introduced only by the measurement, the final measurement, while the evolution of a quantum system, if it's unitary, can be considered as a linear model, but in an extremely large Hilbert space. And here is the main advantage. You have basically a single huge linear layer plus a final nonlinear measurement. And that's what we call a quantum block. And then plus you could add like artificial nonlinearities using these kind of classical layers that you can put before or after it. But the quantum evolution in itself, at least what we considered, is something linear, but huge in terms of Hilbert space. And there is some kind of nonlinearity coming out with the final measurement.
Thank you. Thanks a lot, and thanks again for the nice talk.